This is 10-4 day one. Students will be able to determine convergence or divergence using the ratio test. In your own words, how do you know the following series has a chance to converge? If you take 1/4 divided by 1, that's 1/4, which is less than 1. If you take 1/9 divided by 1/4, in other words, we're taking the second term minus the first term on any two consecutive terms. That is equal to, if we multiply the top and bottom by 4, that's equal to 4/9, which is also less than 1. So if you have a sequence that is decreasing, in other words, 1/9, 1/16, 1/25, those are decreasing, then your series has a chance to converge. And that's really what the ratio test says. It says if you take a sub n plus 1, if you take the second term and divide by the first term, as long as that's less than 1, you have a convergent series. So the ratio test says let this series be a series of non-zero terms. 1, the series converges if the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n is less than 1. And it even works if it's alternating. So if you have a negative over a positive, then taking the absolute value will give you a value that is less than 1. If you kept it as negative, all negative values are going to be less than 1, and the test wouldn't work. 2 diverges if the limit is greater than 1, and then if the limit is equal to 1, the ratio test is inconclusive, and you got to use a different test. Determine the convergence or divergence of the series. Identify the tests or tests you use. There may be more than one correct way to determine convergence or divergence of a given series. Let's go with the limit as n approaches infinity of the absolute value of, let's do the n plus 1 term over. Now if we put n plus 1 in for n, that becomes n plus 2. And rather than divide a fraction, let's multiply by the reciprocal. So we're going to take a sub n plus 1 divided by a sub n, but we're going to multiply by the reciprocal. That's going to be n plus 1 over 2 to the n. That's the a sub n term. We have the limit as n approaches infinity of absolute value of, there's not much we can do with n plus 1 and n plus 2 yet. But we have, let's say we have 2 to the third over 2 squared. So if we picked n to be 2, that's what we would get, and we'd have an extra 2 on top. So this 2 to the n plus 1 means there's an extra 2 on top. And now the limit of this to infinity is like ending behavior. N and n are going to infinity, but this one's doubled. So this one's 2, that's greater than 1. This one diverges. Diverges by ratio test. But you could also do this one. Excuse me, it says there may be more than one correct way. If we do the limit as n approaches infinity, we have 2 to the n over n plus 1. Well, that's infinity over infinity. We have an indeterminate form, so we can do L'Hopital's. And that's going to be limit as n approaches infinity of 2 to the n times the natural log of 2 over 1. So derivative over derivative. And that's equal to infinity, which is not 0. So this one diverges by ratio test. My computer's lagging a little bit, so bear with me. This one right here, we could do limit as n approaches infinity of the absolute value of, and we can take the negative out front, or the absolute value kind of takes care of the negative, so I'm not too worried about the negative. 8 to the n plus 1. There's the n plus 1 term. Let's divide by the nth term, but on this, since it's a fraction, we're going to multiply by the reciprocal. We have an extra 8 in the denominator. So that's going to be 1 over 8. And that is just equal to 1/8, which is less than 1. And so converges, it's really lagging, converges by ratio test. But this is also geometric, where a sub 1 is negative 1/8, and r is equal to 1/8. So we're multiplied by 1/8 every time, which the absolute value of 1/8 is less than 1. So we can say converges by geometric series. Ooh, I got a laggy computer. My apologies. Series. All right. Converges by geometric series. So there is more than one way. Now, you don't have to write every single way that you could possibly prove convergence or divergence. You need to just pick one. Number 34. This one we can't use ratio tests. We have to use, well, this is going to be an indeterminate form, so we're going to use the nth term test for this. And if we plug infinity into n, when we do the limit, that's infinity, and that's sine of 1 over infinity. Now that's sine of 1, that's the sine of 0. So this is infinity times 0. We're going to use the nth term test for this. Limit as n approaches infinity of, let's do this. Let's do sine of 1 over 1 over n squared. Not 1 over n squared, 1 over n. So we created the fraction. We can do L'Hopital's. Limit as n approaches infinity of cosine of 1 over n, and then times negative 1 over n squared. And that's all over negative 1 over n squared. Well, those cancel. And when we plug infinity into n, we get cosine of 1 over infinity. That's the cosine of 0, which is equal to 1. And that is not 0. So this diverges by nth term test. Number 42, we have the limit as n approaches infinity of the absolute value of n plus 1, natural log of n plus 1, over 2 to the n plus 1. And we're going to multiply by the reciprocal, so that's multiplied by 2 to the n over n natural log of n. Well, let's take this one piece at a time. We have the limit as n approaches infinity of the absolute value of n plus 1 over n. So that takes care of this piece and this piece. There's not much you can do with it right now. There's an extra 2 in the denominator, so that puts the 2 down here. And let's take care of the natural log. Well, the natural log of, let's say, 1001, if n was 1,000, over the natural log of 1,000 is pretty much 1. It's very close to being 1. So those, these don't necessarily cancel out. They just, their limit as n approaches infinity is approaching a value of 1. So this is equal to 1/2 because it's ending behavior. We have n over 2n. That's a half. That's less than 1. So converges. And it seems like as I get more ink on here, the slower the computer gets. Converges by ratio test. And then on the next slide, it'll be faster because there won't be as much ink. All right, anyway. Determine, same thing. Yeah, much faster. Limit as n approaches infinity, absolute value of n plus 1 to the 10th over 10 to the n plus 1, then times 10 to the nth over n to the 10th. So now let's, there's not much you can do with those. So that is n plus 1 to the 10th over n to the 10th. There's an extra 10 in the denominator. Now, if we were to multiply this out, like n plus 1 times n plus 1 times n plus 1 times n plus 1, we would get n to the 10th plus something n to the 9th plus something n to the 8th. But if we're taking the limit as n approaches infinity, all I really care about is that the highest power is n to the 10th. It's to the 10. So this ends up being 1/10, which is less than 1. So converges by ratio test. Now, if my theory is right on this, if I clear the ink, this will get a little faster. So if you want to finish writing this down, go ahead and pause the video. I'm going to delete it off so maybe it won't lag so much. All right, deleting it off. This one, we have the limit as n approaches infinity, absolute value of n plus 1 factorial. Now this is really n factorial over e to the n. So this is going to be over e to the n plus 1. It's over e to the n because I'll send that to the denominator, making the exponent positive. Then we're going to multiply by e to the n over n factorial. Now let's kind of discuss, well, there's an extra e in the denominator. Let's take care of that. So an extra e in the denominator. What about up here or down here? How do the factorials cancel? Well, let's say n was 6. That'd be 7 factorial over 6 factorial. 7 factorial over 6 factorial. Well, I can write 7 factorial as 6 factorial and then times 7. That's still 7 factorial. Then over 6 factorial. Now those cancel out, and if n is 6, well, 7 is the n plus 1. It's 1 more than that. So this cancels out to n plus 1. And you could say, well, I have n factorial times 1 more. That's n plus 1 factorial over n factorial. Those cancel out, and we're left with n plus 1. Well, if the top is going to infinity and the bottom is staying constant, this is equal to infinity, which is definitely greater than 1. This diverges by ratio test. Well, that stayed fairly quick since I deleted the ink off of it. This is the exit ticket. If you're following what the class did, then you should do these 3. So go ahead and pause the video. Give these 3 a try. And push play, and I'll review the answers. All right, if you push play, this one is just like the natural log. And I thought the tough part would have been this right here and this right here. That is like the square root of 1,000,000,001 over the square root of billion is 1. This is going to 1, so you can just cancel those out. Then n plus 1 factorial over n factorial is n plus 1, and then there's an extra 2 in the denominator. This one is equal to infinity. That's greater than 1. Diverges by the ratio test. This one, we have an extra 2 on the top. These cancel out with n plus 1 in the denominator, and if infinity is in the denominator, then this fraction is going to 0, which is less than 1, converges by ratio test. And then the last one is geometric. You could do the ratio test for this also. R is a half, absolute value of half is less than 1, converges by geometric series.